time we looked at our at probability theory, and we've almost completed our discussion of probability theory. I still owe you a discussion of one more special random variable called the normal distribution. We'll pick that up in a couple of lectures from now. So our focus is on uncertain quantities. Most of the important things in business we keep track of: profit, cost, revenue, market share, earnings per share, price per share. These things are numbers. In the future, they are uncertain. Uncertain quantities are random variables. They come in two varieties, the discrete and the continuous. For general random variables, they will all be discrete, where you have to take a frequency or a probabilities given and then work out the expected value and the variance. We did look at two special cases that were discrete. The binomial and the Poisson are both discrete. And we looked at one continuous, which was the exponential. And the normal distribution also is continuous, by the way. Every random variable has a probability distribution. It lists everything that can happen and shows you the likelihood of occurrence. And in business, we generate these by collecting empirical data and calculating frequencies. The cumulative probability distribution shows percentiles. It's the probability being less than or equal to some value. And it turns out that's very useful when we go to apply this in the real world. The big point last time was the expected value. Expected value is the long run average, sometimes called the mean value. And for a discrete random variable anyway, we define E of X, the expected value of X, sometimes known as mu, Greek letter mu. We add up each thing that can happen and weight it by its probability of occurrence. And the expected value coupled with the law of large numbers allows us to be able to make recommendations as far as the optimal course of action in decision problems that occur repetitively, that do not involve extreme amounts of money. And expected values are guide to figuring out what's optimal. We have this thing called the variance. All we know now is the mechanics on how to calculate it, and its interpretation we will defer to a later date. But in general, a big variance means you have a lot of uncertainty, maybe a lot of risk if you're investing in something that has a high variance. The more volatility or variability a random variable has, the bigger its variance will be. Variance is denoted V of X, or this lowercase Greek s sigma squared. It has an offshoot and a kin, a relative, called the standard deviation. Some formulas call for the variance, some call for the standard deviation. Obviously, we know one, we know the other. And we also learned that the law of large numbers is our friend. There is no such thing as the law of averages. There is only the law of large numbers. It's all we got to work with to counter uncertainty. Our only hedge against uncertainty is this law of large numbers, or do additional market research to reduce the uncertainty. All right, so that's the theory we went over. Let's do our practice problems before we get into the good stuff tonight. Scotch on the Rocks is a bartender at Tequila Mockingbird. That's cute. Number of champagne cocktails ordered in a night is random and has the following probability distribution. So what did I do? I went out and collected data on the last 100 nights or so for this bar and looked at how many we sold each night. And then I said, what's the frequency of each of those? And I converted those frequencies to probabilities. And I got that they either bought 5 or 10 or 15 or 20. Is that what really happened? No, it didn't. Of course, that's not what happened. but we're just making these problems simple. We're not, you know, if I really tallied them all, it's probably somewhere between, 5 and 30 and every number in between. It's just a bigger, uglier problem, but the steps are exactly the same. And it's because we've made it a simple problem. Simple to work with doesn't mean it's less realistic. We got 30% for 5, 20% time it was 10, 20% of the time it was 15, and 20% of the time, or 30% of the time it was 20. We would have a little difficulty forecasting what would be our demand tonight. What am I going to guess? There's no one with highest probability, is there? I mean, your best guess is either 5 or 20. They both have a 30% chance. If you were going to say, I give you $100 if you can guess tonight's demand, I'd say I'd flip a coin, heads 5, 20, tails 20. That's it. So forecasting just one night, we're not going to be very good at with this particular case. Part A says find the cumulative distribution. Running sum of probabilities, 0.3, 0.3. 0.3 plus 0.2 is 0.5. 0.3 plus 0.2 plus 0.2 is 0.7. And 0.3 plus 0.2 plus 0.2 plus 0.3 is 1. The expected value, probability times value, probability times value, probability times value, probability times value. On the exam, most of the time I'll just say write the expression, and then I will provide a check figure if necessary, if we need to go beyond that. 12.5 is the average per night. So over the next 100 nights, I would guess what? 1,250, 1,250 champagne cocktails will be demanded. So whatever this number is, if I want to forecast any period of time, I'll just multiply the number of days times that to get my forecast for that period. Write the expression for the variance. So I go 5 minus 12.5 squared times 0.3. 10 minus 12.5 squared times 0.2. 15 minus 12.5 quantity squared times 0.2. And 20 minus 12.5 squared times 0.3. And what the variance is the expected squared distance from typical value of the population of the random variable to its expected value. Yes, sir.
Earlier you added up the percentages. Why is it that we added up the percentages to get that distribution?
The cumulative.
Yeah, the cumulative.
Okay, so how do I construct the cumulative?
Yes.
The only one way to construct it. It's a running sum of probabilities. What's the probability if that demand will be 15 or less? 20% of 15 on the dot, 20% for 10, that's less, and 30% for 5, that's less also. So the way you'd read this is the probability that x is less than or equal to 15 is 0.7. So here's your value, here's the cumulative probability. So that's saying the probability x less than or equal to 7 is, less than or equal to 15 is 0.7. Yeah, that's how you construct the cumulative distribution. It's a running sum of probabilities. All right, so we get $5. Whoa, that's cheap. For champagne cocktails, what's the expected revenue? Well, the revenue is, how do I get the revenue if I sell 5? 5 times 5, okay? 10 times 5, 15 times 5, 20 times 5, 25, 50, 75, 100. See that increments the same each time? There's 25. That's a linear transformation. We just took 5 times whatever our quantity sold was and convert it to revenue. So I can use Rule 7 to say that the expected revenue, which is equal to 5 times X, is equal to 5 times the expected value of X. And I know that the expected value of X is 12.5. So I have a quick, easy way to find the expected revenue. And that is $62.50. Now, champagne costs us $6 a bottle, and we can make 10 champagne cocktails out of each bottle. Any open bottle of champagne is discarded at the end of the night. That's not what happens to it, folks. That's the after closing party. That's the first thing that goes then, because that's when the place starts really hopping. It's 2:01 a.m. I've heard. I have no personal knowledge of that. Yeah. The fact that they have a picture of someone who looks remarkably like me at the door saying customer of the year is an absolute coincidence. Yeah. Just, yeah. I have an evil twin that seems going around everywhere. I don't know. So I need 5 drinks. Cost me what? $6? I sell 10 drinks. Cost me $6, 1 bottle, huh? Sell 15 drinks. Pop another bottle, $12. 20 drinks. Pop another bottle, $12. Okay. So my profits are 25 minus 6, 19, 50 minus 6, 44, 75 minus 12, 63, 100 minus 12, 88. From here to here, we drop how much? Is that 25? Then 19, then 25. It's not a linear transformation. They're not all the same. I do not have a quick way to do that. I got to do it longhand. So I go 19 times 0.3, 44 times 0.2, 63 times 0.2, and 88 times 0.3, and I get 53.50. Some of you probably said, well, hey, I need, what, 12 and a half bottles, right, on the average? I'm going to sell 12 and a half drinks. How many bottles of champagne do you need to do 12 and a half? 2, not 3, 2. Well, that's just it. Well, you had to, anything over 10, you had to open another bottle, right? Right, but it doesn't work that way. So you just can't take 62.50 and subtract $12. That doesn't work. What you could have done is the following. You said, what's my expected cost from the, hold it down, please. What's my expected cost for supplying the champagne? Well, I got $6 with a 0.3 chance of happening, $6 and a 0.2 chance of happening, $12, 0.2 chance of happening, $12 and a 0.3. Multiply those out and your expected cost is $9. Half the time, so the probability just happened to be half here. Half the time it costs you $6, half the time it costs you $12, costs you $9 on the average. So 62.50, who typed that? Who did type that? Minus, catch that typo, 62.50 minus the $9 is 53.50. So a couple ways to do it, whichever way you did. If you were successful in getting the 53.50, then you're in business. Any questions on that one? Fabulous. Then we had our first special random variable dealing with the number of successes we have in a certain number of tries. And it's the binomial developed by that wonderful human being, Jakob Bernoulli. Jakob was not a nice guy. To know him was to hate him. They say the same thing about my brother-in-law too, by the way.
What are you doing?
I do, yeah. I do, yeah. And we're looking at the number of successes in a certain number of tries. It is discrete. It takes on the values 0 and 1 and 2 and 3 because we're counting the number of successes, whole numbers only, and it has an upper bound. Expected values given by NP, where N is the number of tries and P is the probability of success on each try. And the variance is N times P times 1 minus P. And we said the primary application of the binomial distribution is a couple of them. Number one is it models consumer behavior where they're coming in with appointments and they either purchase or don't purchase a product. And the other good application of the binomial is most of quality control deals with the binomial distribution, where the part either meets specifications or it doesn't. It's either a good part or a defective part. So we use the binomial distribution extensively in quality control. Our example of the binomial is page 3, number 6. D. Presence, who owns D's Pharmacy located in a small medical office building. She estimates 20% of her prescriptions are referrals from Dr. Mel. For the next 25 prescription customers, what's the probability of that? Whatever, whatever, whatever. So letting X equal the number of referrals from Mel. And you do need to put your notation on all of the problems on the midterm and the final. You begin each problem by using the word notation. Define your terms as you develop them. Letting X equal the number of referrals, we know it takes on the values either 0, 1, 2, 3, 4, up to 25. It is binomial. 25 repetitions, each has a 0.2 chance of success. What is the probability of seeing 6 or fewer? If it said 6 or fewer, we'd write that. If it said at most 6, we would write that. So the two terms that get you a less than or equal to 6 or fewer, at most 6 give you a less than or equal to. 6 or fewer, at most 6. Those two terms tell you it's a less than or equal to. Less than or equal to's are direct table lookups in our table because every one of our tables is a less than or equal to a cumulative distribution. So I head to my tables. Hopefully you all found the tables on the workbook module of the course. So I go to 25. Well, first I found the 25 repetitions, 0.2 chance of success, and I think it was asking 6 or fewer, 0.7800. 78% chance that we will find in the next 25 prescriptions, 6 or fewer were referrals from Dr. Mel. If it says between, I would write 3, less than or equal to X, less than or equal to 6. Between 3 and 6. This is how we write the expression between 3 and 6. So I want 3, 4, 5, 6, 7. I'm sorry, 3, 4, 5, 6. So into a hat, I drop what? What did I just drop into the hat there? 0, 1, 2, 3, 4, 5, and 6. Just went into the hat with that. I just dropped 0. through 6 into the hat. Now I get rid of the undesirables. I want to get rid of 0, 1, and 2. I get rid of them by removing that chunk. That remove, that minus these, remove 0, 1, and 2. Now left in the hat is 3, 4, 5, and 6. So for the binomial and the Poisson, when you do a range, you just bring this one over here, look that one up in your table, then bring this one over here and drop it down by 1, because the 3 is a keeper. We want to keep 3 in there. And if you put 3 or less here, you would remove the 3. So we want to keep 2 or less. Okay. You could say less than 3 here if you wanted to, but since it's discrete, if it's less than 3, it's less than or equal to 2. And we look up less than or equal to is we look up 2. So I get the 7800 I had before, then I go back to my tables and I pick up the 2 here, and the 0.0982. I got it right. Question, yes? If you put a 3 here, there a big red mark would appear by that answer, because you've removed 3. You found 4 through 6. Okay. So we wanted 3 through 6. 3 is a keeper. Don't get rid of it. If it said more than 4, if it said more than 4, 4 or more, you would write this. This is a statement of 4 or more. We don't have a greater than or equal to table. All we have is a less than or equal to table, so I got to use what I got to solve it. I take 1. What did I just throw into the hat there? 0 through 25 went in the hat. At that. Everything went into the hat. That bought me 0 through 25. And now I remove 0, 1, 2, 3. That's it. 4 is a keeper. Remove 0, 1, 2, and 3. So for greater than or equal to's, you go 1 minus, and then you again drop it down by 1, because you don't want to take the 4 out. You want to get rid of 3 or fewer. If it says equal to 5 or exactly 5, what's probably that x is exactly 5 or equal to 5? That's just a really narrow range, right? That's 5 through 5. We do the same thing if I'd written 5 through 5 here. Use this exact same logic. You go 5 or less minus 4 or less. That would just leave 5 in the hat. D makes $10 profit per prescription, but has to pay Mel a $3 kickback on referrals, which is blatantly illegal. Blatantly. But people still do it. One of the, I made a mistake when I had my business of, well, before I had my business, I was called in as a consultant on a job for another company, and their client was a ambulance chasing lawyer, personal injury lawyer, who he and his wife took pride. They were known in the insurance industry, called them Bonnie and Clyde, is what they referred to these couple as. That's how blatant they were. And he was doing his first information system, and he had a requirement in there. We had to keep track of where the referrals came from, where it was an ambulance driver or even at cops, other people were bringing them business. And then it's illegal to pay a kickback, but the size of the Christmas present was exactly proportional to the number of referrals, the amount of money that those people brought in for them. So luckily the company I was working for had a falling out with this individual, and they ended up suing each other. And I wasn't involved at all, luckily. And he asked me if I would leave the company and finish the system for him on my own. And I said, no, thank you. I'm a loyal person, right? I really wasn't, because I later broke away from that company and started my own business, but there's no way in hell I was going to work for a lawyer. I mean, it's like being nothing personal to lawyers. There's great ones out there, and some of them do great work for, wills and stuff like that, but there's just too many of them, and they do what they know how to do, and that's sue people. And I had never had trouble with any one of my clients getting paid except the American National Red Cross. I had trouble getting, instead of going by what we all agreed to in meetings, they referred back to the written document. That's all they would ever refer to, because their entire management was lawyers, run by lawyers. And just their mindset is, it's not what you agreed to, it's what's on paper, which, well, that's okay, I guess. But finally, we got paid off. All right, so what's my expected profit? Well, if we didn't have to pay Mel off, we'd make 10 bucks times 25, 250 bucks from the next 25 customers. But we have to pay Mel off, and that's 3 times X, however big X is. Well, what is this? This is a linear transformation. 250 minus 3x, that's a linear transformation. So I can apply my rule 7 and say that's 250 times 3 times the expected value of x. And then I go back and look, say, oh, for the binomial, what was that formula again for the expected value? It was 25 times 0.2. That's the formula for the expected value. NP, 25 times 0.2. So that's where I got those. So any question on our binomial problem? Great. Just take a second here. Here's our buddy. Anyway, here's the picture. Looks like he's sucking on a lemon, huh? This is on a good day. Bernoulli was not a very nice person, but he was normally. So why was he a bitter man? Well, normally under any circumstance, he would have been the smartest scientist alive at his time. Would have been far and away the smartest scientist alive. But who did he live in the same time frame as? Isaac Newton, probably the second smartest scientist who's ever lived. His stuff was maybe 100 years ahead. And that was his development of physics and calculus. He developed both of those, and it would have been another 100 years before anybody would have accomplished what he did. And he only spent maybe 20% of his time on it, because he spent most of his time on alchemy. He was trying to make gold from lead, and on theology. He was trying to, he thought there was a code in the Bible, and he's trying to break it down. And so he spent all his time on that instead of working on physics and math and other scientific endeavors. And he would have set us another couple years ahead of that if he'd really applied himself. And the other person who was alive at that time was Leibniz, the co-inventor of calculus, who was a true Renaissance man. He was good at everything he touched. He was brilliant, and he also he worked for the ruler of Germany, I think, or something like that, who was interested in his family tree, and had Leibniz doing all this stuff on his family tree when he could have been, doing these magnificent things and pushing the boundaries of science. And then there was his brother, Johann, who was just as smart, maybe even a little smarter than Jakob was. So Jakob was not a nice person, as I said. He and his brother tried to work together the first couple of years, and then they, like me and my brother-in-law, they had a falling out, and they did not like each other at all. And they, instead of, like me and my brother-in-law, we get drunk at family things and, try to physically assault each other. Instead of doing that like normal cultured people would do, okay, here's what these guys would do. They would hurl mathematical challenges against each other. Solve this, mother, This is literally true. They would formulate, one of them would figure out something, and then he would put out this challenge, his veiled challenge to the world to solve this, and then hand deliver a copy to his brother. So, true story. All right, onward to a nice guy, Simon Denis Poisson. By all accounts, he was a pretty decent person. He developed the Poisson distribution, and here we're looking at the number of occurrences through time or space of a randomly occurring phenomenon. And it's, clicks on a Geiger counter, it's births, deaths, people walking into retail outlets, hits on your website. These things all just happen randomly. Earthquakes in California.
Just to put it in very sort of like to the thing that we went, discrete would be there's a number of accidents that are going to happen due to texting, but it's unlimited and the amount that can happen. Would that be just an observation?
If you're looking at the number of accidents that can happen, or the number of claims that against an insurance policy, that is a discrete random variable. Okay. And accidents do happen randomly. So it is a good application for the insurance industry, yes. And the time between accidents or claims is roughly exponentially distributed. That is true. So it is, both of these are distributions that are looked at in the insurance industries. The parameter is lambda, lowercase lambda, and that's the average rate of occurrence. And T is the number of time periods. Sample space is how many occurrences did we have in T time periods. So we set an alarm clock, say wake me in T time periods from now, and in the meanwhile you count each occurrence on your fingers and toes, 0, 1, 2, 3, 4, discrete and infinite. The expected value is lambda times T, but the variance also is lambda times T. If we change our focus from counting for a fixed period into measuring exactly how long it takes the next occurrence, then that changes us from discrete to continuous, because time occurs in a continuum. And we have one parameter, still lambda. And T is the time until the next occurrence, or equivalently, the time between occurrences, either one. And the formula for that is expected time is 1 over lambda. The variance for time is 1 over lambda squared. So when the midterm comes around, what, weeks from now, 3 weeks in the 8-week session, and a problem says something occurs randomly at a rate of something. Okay. We know immediately that it's either a Poisson or an exponential, right? As soon as the problem says something occurs randomly, that will be a Poisson or an exponential. Yes? Okay, good question. What's the difference between the capital T and the lowercase t? It's a very subtle one. I do this so that I stay correct with if a real statistician saw it. But for you, just write a big capital T in there. That's great. The subtle difference that statisticians have is capital T is the concept of time. The little t's are actual values of that random variable. The little t's are applications of it. Is it 30 minutes? Is it 40 minutes? Is it 50 minutes? Where t represents all time that might occur. That is the difference. Well, the sigma, no. The sigma, the capital sigma we use to meet summation. The lowercase sigma we use for the variance and standard deviation. The variance and standard deviation, we use the lowercase standard deviation sigma. So how can we screw this up then? You know, because it's going to be pretty easy to tell. If I say randomly occurring and you can count them, then it's Poisson. If you need a stopwatch or the measuring device, it's exponential. So how else could we screw it up? You could get lambda wrong. So let's solve that problem right now. How are the different ways that lambda can be specified? Machines break down at a rate of 4 per hour. Okay, start over. So we're at the midterm, right? And a problem we just read a problem and it says such and such occurs randomly. We know, and it doesn't give us any other data except some rate of occurrence. So we know that's either Poisson or it's exponential. As soon as it says occurs randomly. The word occurs randomly means it's Poisson or exponential. If we count it, it's Poisson. How many? It's Poisson. How long? Stopwatch is exponential. How many is Poisson? How long is exponential? So then, what else could I get wrong in the problem? Well, you might screw up on your lambda. So let's fix that right now. Machines break down randomly at a rate of 4 per hour. Lambda is 4 per hour. Number 2, machines average 15 minutes between breakdowns. Is there any difference between statement number 1 and statement number 2? No, there is no difference between statement number 1 and statement number 2. Statement number 1, if they're happening at a rate of 4 per hour, how long do you have to wait to see a breakdown? 15 minutes, 4 per hour. There's 4 15-minute increments per hour. Same statement exactly. So we know it's 4 per hour, right? That's one way to look at it. But what we've actually said is it's 1 every 15 minutes is the rate. It's 1/15 per minute. You've told me 1 every 15 minutes. You've actually given me the expected value. You've told me that 1 over lambda equals 15. So to solve for lambda, turns out it's 1 over 15. And they are the same. To convert minutes to hours, I multiply by 60, right? And I get that, there's your 4. So those are identical statements. A rate of 1 every 15 minutes is the exact same thing as saying 4 per hour. Which one would I use? Whatever the problem is. Once if the problem is talking about hours, I'll do it in hours. If it's talking about minutes, I'll do it in minutes. Okay, so what's the trick? If it says how many, that's lambda. Number 1 said how many, right? 4 per hour. What did number 2 say? How long? How long did it take? If it says how long, gives you a time, you take 1 over that. There's the trick. Okay, try it out, see if you can get it. We in LA averages a murder every 12 hours. I think that's roughly accurate. Chicago, what is it, like 12 per day, every 2 hours? Did I say how many? Or did I say how long? How long? So it's what? 1 every 12 per hour. Also known as what? 2 per day. 2 per day. 2 per day. California averages 3 earthquakes above a 4.0 each month. Did I say how many or how long? How many? So you just write 3 per month. That's all there is to it. Once again, if they tell me my rate of occurrence is how many, that's your lambda as is. If they say how long between occurrences, then you go 1 over that.
So Professor, 1 and 4.
No. Wash your mouth out. Shame on you. Okay. Okay, our discussion here is what's lambda. It has nothing to do with whether or not the problem we have to solve is found in the Poisson table or the exponential table. This, no, I have no idea which one it is. I have no idea at all by this. You know, if in number 1, if it says how many occurrences in the next 3 hours, Poisson. If it says, you know, what's the probability that we see a breakdown the next 20 minutes? That's exponential. So, I don't know which I don't know which one of the problems it is. But.
So all this is how long? All this is how long?
Number 1 and number 4 are how many. How many happened? 2 and 3 are how long. All right, let's go ahead and solve our 2 practice problems here. Bo Liebig and Anorexic own Bo and Anna's Diet Foods. Customers come in randomly at a rate of 4 per hour. What's the probability that the number of customers between 3 and 6 p.m. today is whatever. Okay, so it says the magic words, customers enter the store randomly. Okay, it's asking me for part A anyway. How many? What's the probability that it's 16 or less? So it's how many. So it's Poisson. X is Poisson. The number of customers in 3 hours. Our lambda, it said how many? 4 per hour. So lambda is 4, and I'm going to sit here and watch it for 3 hours for some reason. Our expected value is 4 times 3 or 12. That's the expected number of people coming into the store we have in 3 hours. And it's also our variance. What's the probability of 16 or fewer customers coming in this 3-hour period? So we'd make our way to our tables. And we'd go to a lambda T of, getting warm red hot on page 10 of our tables. We find lambda T of 12. And then I go to, we wanted 16 or fewer. Okay, 16 or fewer, and the 12 column labeled 12 here, lambda T of 12, and the 16th row, 0.8987 is the value I find. 8987, got it. Everybody see that okay? Great. Between, yes?
Is it only for Poisson that the expected value and the variance have the same?
Poisson is one of the very few distributions for which that's true. It is the only prevalent, common, special distribution that's true. But we could make up a distribution that would be true for, but it wouldn't be any of our special cases.
Just taking into account what we're studying. Are we applying this formula just for Poisson?
Are we applying which formula just for the Poisson?
You know, the lambda T.
Well, I didn't need to, that wasn't asked for it at any point. You would not have need to, I just put that in to show off, okay? I didn't need that. I needed to find the 12 to use the table, okay? But I just thought I'd throw in the tidbit that, by the way, the variance is also equal to 12, because for the Poisson, it's one of the few distributions for which that's true. But no, I didn't need to put that in there. I shouldn't have, because then you ask the question. That'll teach me. Between 9 and 16. Do it exactly the same way you did the binomial. I take 0 through 16 and drop it in the hat. Okay. And I get rid of 0, 1, 2, 3, 4, 5, 6, 7, and 8. That got rid of 0, 1, 2, 3, 4, 5, 6, 7, and 8 right there. Thus leaving 9 through 16 in the hat. So we would have looked up the 8 here and on the table and get the point. 1550. Let's do that just for the heck of it. 8 and 13. Did I get the right value? Ooh, there it is. 0.1550. Greater than or equal to 17. 17 or more. 1 minus 16 or less. So we put all of them in the hat. And by the way, there was an infinite number of them this time, because the Poisson has no upper bound. So 1 minus x less than or equal to 16, 1 minus 0.8987. It takes the cashier an average of 10 minutes to check out a customer. Wow, that seems long, but we're probably, educating our customers on the health foods and all that good stuff. What's the probability that the time to check out the next customer is? So now I switched. Now I'm looking at an exponential. I want to know how long it's going to take to check out the next customer. That's exponential. I still need to find out a lambda. The lambda says it takes an average of 10 minutes to check out a customer. Did I say how many or how long? How long? 10 minutes. So my lambda, is going to be 1 over 10. 1 every 10 minutes. So the lambda is 1/10. Per minute. And, it's a good thing because it's asking me in minutes. What's the probability that check this person out in 15 minutes or less? So It's less than or equal to use our exponential tables, I need a lambda t value. 1/10 times 15 is 1.50 is our lambda t value. 1/10 from up here and the 15 from right here. And so we look at the next table. 1.5, 1.50, 0.7769er. Between 5 and 15 minutes to check out. Okay. Take 15 or less, so into the head I put an infinite number of values, all the values between 0 and 15 minutes from now. And I take out what values? All the values less than 5.
When you're supposed to take one, you're supposed to put all of it there. Go down one.
Huh?
5.
Yeah.
It's supposed to be 4, right?
Is it supposed to be 4?
12 5.
No, because it's continuous. There's 4.5 minutes, there's 4 3/4 minutes, and there's 4 minutes 50 seconds, and you got rid of those, and they're less than 5. And you got rid of them when you dropped down to 4. Well, I don't drop down at all on the exponential because it is continuous. So technically, it should just say what? It just should say what? It should just say less than, huh? But we don't have a less than table. We have a less than or equal to table, right? What's the difference between, I didn't draw the picture here. Right? Did I draw a picture here? Oh yeah, okay, here's the exponential distribution. So let's suppose this is a 5 here, okay? So what's the difference in area between less than 5 and less than or equal to 5? They're infinitesimally close because one of them has the 5. What's the area under a point? It has height, but infinitesimally small width. So they're infinitesimally equal to each other. They are, to an infinite number of digits, equal to each other. So that's why we don't drop it down at all. So I've got the 15 minutes. Let's get the 5 minutes here. 5 minutes times a 10th, 0.50. I head to my table here and look up 0.50, 0.50, 0.3935. And then so on, greater than or equal to. All right, here's one we haven't done yet. And you need to know this for simulation. Anytime I simulate, I'm going to look up, I'm going to be given a percentile and then simply look up that percentile. That's all simulation is. You're randomly given these percentiles, you look them up, and then you say what happened. Find me the 95th percentile. Now, the probability of us being checked out in what time is 95% or less. Head to my table. All of our cumulatives start small, like at 0, and get bigger. And this one goes to almost 1. So to find a cumulative in any of our percentile, in any of our tables, I want the 95th percentile. I go down, go down, go down, go down, go down, go down, go down. Oh, is that the first one bigger than or equal to 0.9500? Let's double check here, go to the last row. Yep, that's the first one bigger than or equal to 0.9500. So we know what? We know our lambda t is 3. Our lambda t has a value of 3. Okay, so our lambda t has a value of 3. But our lambda is 1/10. T, I don't know. So I get a little equation, 1/10, t equals 3. Multiply both sides by 10. And we get t equals 3 times 10 or 30 minutes. So 95% of the time, customers checked out in 30 minutes or less. It still doesn't sound too good. Maybe it's, I still don't see how you make that sound really good. We spend so much time with our customers teaching them about being healthy that 95% of our customers check out in 30 minutes or less. Okay, any question on that problem? You.
For number E, or letter E, when you were doing the lambda t, why did you do 5?
What?
Second row.
Right here?
Yeah, but like the second row to the right.
Over here?
Doing lambda t, why did you pick 5 minutes to multiply it?
Oh, because I'd already done the one for 15 up here, right? I did the 15 up here. You got to do them both, but I had one from before. Part D did half the problem for me.
Oh,
Yeah. If I'd done 5 to 10 minutes, do them both. Got to do them both. I just got lucky that I've done them before. Actually, it was my dear and beloved prof looking out for his flock. And on exams, he minimizes your work because he reuses stuff from other parts of the problem. What a swell guy. What a all-around good fellow. How come his reviews are so horrible? I don't know. Okay, let's do the last one. Shirley owns Kinky's Copies. Provides 24-hour-a-day duplicating and printing services. Got self-service thing. It averages 200 hours between breakdowns. What's the probability in the next 30 days, 720 hours, there will be this many breakdowns? All right, so part A is asking 5 or fewer breakdowns, 4 breakdowns. So it's a Poisson because it's asking how many are lambda. That's a different matter entirely. It's an independent discussion. What's our rate of occurrence? It says once every 200 hours, or it averages 200 hours between breakdowns. Is that how many or how long? How long? 1 over 200. All right, so my lambda is 1 over 200. My t is 30 days. I have wrong times there. They don't match. I got hours and days. So I did the conversion for you. The 24 hours, 1 day is, or 30 days is 720 hours. Here, before I get a question, let me fix this. You sit at the back. Okay, so lambda t, 1 over 200 times 723.6. Less than or equal to 5, 5 or fewer. Straight Poisson, 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 just all the regular stuff. Pretty much repetition at this point. Then I switch to time until next breakdown. Now it's switched to the exponential. My focus is not on how many breakdowns happen, it's how long until the next one, and that is exponentially distributed. 160 hours or less, we take 1 over 200 times the 160, and I get 0.80. And I went in and looked at that in the exponential distribution. 0.80, 5507, 5507, and that's pretty much it. Okay, so that's our discussion from last time. Hopefully those are becoming good friends for you. I know, for some of you it's culture shock, having not dealt with any kind of this sort of material for a long time, if ever. Just don't psych yourself out. I have a very good success record of getting people through this stuff as long as they give me a fair shot at it. It may take a couple of weeks, it may take 3 weeks. You just keep going over the problems, going over the problems, going over problems, and pretty soon, aha, got it. So the proverbial light will go on. Okay, any questions of anything? Let's do a logical break point. Let's go ahead and take our 20-minute break, and then we'll reconvene at 9 o'clock. Can we just make it 9 o'clock? We'll reconvene. Very good. Thank you. See you. Yes. Hold on. Before I start cursing.